Okay, for a discrete random variable, a lot of this you already know. The key to this is that discrete means that there's like a fixed number of values or a fixed set of possible values. The next idea that we're going to do is continuous, which means, an endless amount of possible values. For discrete, we're doing a fixed set. So we're going to have numbers like from 0 to 5. They're not going to go forever. And basically how we can organize them is we're going to organize them in a table of values. And it's called a probability distribution chart. And what we're going to be doing is we're just going to be kind of organizing. We have a value that we're going to be putting to something, and then we have its probability. We're going to give the values numbers like for x, however many we need. Now keep in mind that we're going to have a fixed number of them. They're not going to go on forever. And then we're going to have its probability of each one below it. So let's try kind of an example so you can kind of see how this works. Let's say we were going to toss a fair coin 4 times. Let x equal the number of tails you get. So if we were going to toss this 4 times, we'd have 4 type of possibilities. When you flip the coins, we could have heads, 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 heads. That would actually have 0 tails. So if I were to be setting up a table, I would put value, and for x1 maybe 0, which would mean 0 tails. 1 tail, 2 tails, 3 tails, 4 tails. And then its probability. So you can think of a probability chart. You can list all of these out. It's up to you. But the probability of me getting a 0 or 0 tails would be only this one shot. And when I think of my probability for this, it's out of 16 possibilities, so my probability is 1/16. And you could also put that in a fraction. You could put 0.0625. Don't put percentages here, okay? Let's stick with numbers between 0 and 1. So fractions or decimals. The probability of getting 1 tail. So think about it. It could be tails and then 3 heads. It could be a head, a tail. It could be a head, and a tail. It could be a head, 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 and then a tail. So there's 4 different possibilities. To get 2 tails, I could have a few different ways to calculate to get 2 tails. I'm going to kind of work backwards. To get all 4 tails, it would be 1/16. And to get 2 tails, you could do it a few different ways. And again, I'm going to kind of work backwards. To get 3 tails, I can kind of think of the same way over here. It's going to be the same old probability because I want to picture 3 tails. So if I just replace all the heads with tails and all the tails with heads, I can kind of see the probability of getting 3 tails would be also 4/16. And I think that leaves 6/16 left to be 2 tails instead of writing them all out. So we could do a variety of things with this, but this is called the probability distribution chart. Now, keep in mind, you don't want to just, when we're finding different values, we don't want to just find, let's say we're finding the mean. We're going to call the mean mu of x. and that's a terrible view, but, and it's just, the problem is we don't want to just work with the values. We don't want to say, even though it works for this one, let's just add up 0, 1, 2, 3, 4. It's actually, we need to find the value and probability of it to sum up the mean. So technically we would want to do 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16. We want to multiply it by its probability so that it's distributed and the weight is given. Just in case we have something that's skewed, we would want something more represented. For this one, we want 2 most represented because it has the majority of the probability of being selected there. So another way to write mean would be the sum of xi pi, which is the multiplication of x and p, the value and its probability. And so what it would look like would be the probability of those multiplied by the value of it and added to the second one and the third one, etc. Sometimes this is also called the expected value. If you were to continue this for a while, you would see that it would be the after many repetitions, this would be the expected value. And it also is sometimes called E of x. So that all technically kind of means the mean of it. You can also put this in a histogram where you have the probability on one side and you have the x on the other. And so we'd have 0, 1. And remember, we want them evenly distributed. And the probability, we could put 6/16, looks like that one's 3.375. Actually, I mean, to make it easier, we could do 1/16, 2/16, 3/16. And we can do all that work that we had done from chapter 2, I think it was, when we talked about is it skewed and things like that. You can find more out about it. And compare and try to find the mean and where's the median lie, all those like key things that we had done before in chapter 2 kind of get recycled here. Continuous variables is actually a little bit easier, but first let me take a minute and say, can you calculate something like this, the probability that x will be greater than 1? So the probability that you'll get more than one tail. When I say it like that, hopefully you're getting the idea. Because the x was the number of tails that you get. So we would want 2 tails would work, and 3 tails would work, and 4 tails would work. We would just be summing up their probabilities. And in order to make sure that we are that we have a valid probability distribution chart, just like always, all these probabilities should sum to one whole. That's why I want you to keep it not in percents but in decimals or in fractions. They should all sum to 1, and each one of these values has to be between 0 and 1, just like every probability is always between 0 probability, or 0 and 1. 0 probability being it would never happen, and 1 being it's a for sure that it would happen. So for surely, this whole thing is 1 because that gives you every single outcome possible. Continuous variables are a little bit different. It is exactly what we were doing before. For this, there isn't a fixed set of possible values. There is basically an infinite. And all we use for this is our density curve. So we want to imagine this normal curve. And remember, the probability under a normal density curve is always 1 for the whole thing. And you should be given what the mean is. Let's say the mean is 30.7. And the standard deviation is 2.7. You can build kind of your where things lie, 30.7 here, and then up 1 and down 1 would be 1 standard deviation, up and down. So down 2.7 would be like 28, and up would be 32, 33.4, something like that. And for these types of problems, let's say we would be trying to find out the probability that x is greater than or equal to 30. You would want to say, okay, where does 30 lie? Somewhere over here. And I want it greater than. We would actually be using that table in the back of the reference charts. And we need to do the z-score. So keep in mind the z-score is the actual minus the mean over the standard deviation. Or for this case, we're going to use sigma. So the z-score would be the actual is 30. And don't worry about this greater than or equal to. It doesn't matter if it's that or if it's just greater than on it. Minus the mean, 30.7 over 2.7. So this should be negative 0.7 over 2.7. And we need to do some math and grab that table. So I'm getting a z-score of around negative 0.25, something like that. And I need to use my chart in the back of the book or the back of the reference charts to see what that actual probability would work out to. Now when I do this and I look it up in the back of the book, I'm getting about 0.4013 equals, the probability would be 0.4013 for the probability. But when I look at this chart, doesn't it look like it's 50%? I mean, more than 50%. So 40% doesn't really make sense to me. When you look at the chart in the back of the book, keep in mind, it's going to be giving you to the left. So you have to actually use that complement rule of the whole thing is 1, take away the 0.4013, and it would actually be something 0.5987, something like that would be your final probability for something like that. So that's why when we're going to do a practice at the beginning of class, and hopefully we were able to accomplish that. Even if you were given a range and not the whole entire thing, you could calculate them even if we were to stop somewhere like here and find the space in between by doing subtraction.